Hi there. We're going to start a new unit today. It's called Redox and Electrochemistry. We're going to try something new with this unit in that the lessons that we see will be seen at home, and the practice problems that we do will be done in class. Let's take a look at our first topic. How are oxidation numbers assigned? Today I'm going to teach you how to assign ownership of valence electrons in 4 special cases. There's the uncombined element, the simple ion, the compound, and the polyatomic ion. In our first case, uncombined elements, what you need to know is that among like elements, valence electrons are shared equally. So that means that the oxidation number is 0. So when we look in our first example here, hydrogen gas, there are 2 particles of it joined together. Each one has an oxidation number of 0. In our next example, where we have some sodium metal in the solid state, so it's many, many particles of sodium that are all together. They will share their electrons equally, so in this case, the oxidation number is still 0. In this case right here, where we have sulfur with an 8, I did not give you the phase, but it's not important. What you need to know is if that sulfur is teamed up with identical particles, they are going to share their electrons equally, and the valence electrons, as I said, will be shared equally, and the oxidation number is 0. In the next case, the simple ion. This is actually really simple because all you need to know is that the ion charge is identical to its oxidation number. So for example, if you have a sodium ion that's dissolved in water, the ion charge plus 1 is the same thing as its oxidation number. In this next case here, where we have a zinc ion that's dissolved in water, this is another case where the ion charge plus 2 is identical to its oxidation number. In our final example, we'll just mix it up, so we have some negative ions as well, dissolved in water, but the -1 of its oxidation number is identical to its ion charge. Now, in compounds, you need to understand that we are going to be having unlike elements that are combined. In this case, the electronegative, or the more attractive element, is the one that gets assigned the electrons. The other thing that you need to know, the sum of the oxidation numbers of each element must add up to 0. So let's look at our first example here. We have sulfur dioxide. So the way that I've set this up, since it is a compound with no overall charge, it must be equal to 0, and then the oxidation number of the sulfur plus the oxidation number of 2 oxygens must add up to that 0. Now here, you're going to need to look at your periodic table. Up in the top right corner of the oxygen, you will see that it has 1 ion charge only. So that's what I plugged in here. The -2 ion charge for the oxygen then gets multiplied times 2 plus the sulfur, and it sums to 0. On the next line, I'm just combining terms. 2 times -2 is -4. So sulfur minus 4 is equal to 0. We need to solve for our unknown sulfur, so I added 4 to both sides. And so I found that sulfur's oxidation number is +4. By convention, frequently you will find that people write the oxidation number directly above the element in each case. Now, something that I want you to see, overall the oxygen contributes 4 negative charges, but each oxygen only has a charge of -2. You must confirm that the charge you write here, or the oxidation number, is something that is found in the periodic table. Let's take a look at another one. This next example is a little bit more tricky because the iron, which is found in the center of the periodic table, can be multiple positive ions. We're going to have to do some detective work to figure out which one is the correct response. So again, because it's a compound with no overall charge, we set it equal to 0. There are 2 iron particles plus 3 oxygen particles. We refer to our periodic table where the oxygen is a -2 charge. We plug that in. 0 is equal to 2 of the irons that we do not know, plus 3 times -2. I combined my like terms and I found that this is a -6, and I just continued that from the previous line. Since I want to solve for this unknown iron, I add 6 to both sides. Those cancel out. 2 Fe are equal to +6. +6 then gets divided by 2 on both sides to get the Fe all by itself. I then find that the charge of the iron is +3. When I refer back to the reference table, I see that +2 and +3 are my options, and in this case, I know that the +3 is the correct answer, and the -2 for the oxygen. Okay, in our last different case, polyatomic ions, we're going to combine what we knew about the simple ions with what we know about the compounds. So again, between unlike elements, they're not going to share equally. The more attractive or more electronegative element gets assigned the valence electrons. The sum in this case of the oxidation numbers is going to be equal to the ion charge. We are not summing to 0 as we did in the previous examples. We have as our first example here the carbonate ion. It is 1 carbon, 3 oxygen, and overall this particle has a -2 charge. So starting with that -2 charge, I then say that that is equal to 1 carbon charge plus 3 of whatever charge the oxygen has. I then plug in the -2 for the oxygen and continue all the way across. I combine the terms that I can. -6 over here is equal to a -2, and the carbon there in the middle. I then need to get the carbon all by itself, so I add 6 to both sides. Once I've added 6 to both sides, I find that carbon has an oxidation number of +4. You can check your periodic table and you'll find that +4 is one of our options. So I will write that with the +4 directly above the C and the -2 directly above the oxygen. Let's look at one final example. In this case, we have the ammonium ion. This ammonium ion has a +1 charge. It contains 1 nitrogen, 4 hydrogen, and overall it has that +1 charge. So we set it equal to +1, 1 nitrogen and 4 hydrogen. Now in this case, hydrogen has 2 charges listed, but I'm going to give you a hint. In our class, hydrogen is always +1. So I put in a +1 there, and so then I combine the terms that I can. +1 equals N plus 4. I then subtract 4 on both sides, and I find that the charge of the nitrogen is a -3. I then write the -3 directly on top of the N, and a +1 directly on top of the hydrogen. This is a little bit different than the ones we have seen before. It is generally written so that the positively charged particle is written first. But in this case, as it turns out, the nitrogen is the more attractive particle. Now, I've given you all the instructions that you should need. I'd like you to try these, write them down on a piece of paper, and bring it to me in class tomorrow. I would like you to determine the oxidation number for the chlorine in each of these examples. We have Cl2, Cl-, Cl2O, KClO3 and ClO3 minus 1. Good luck.